basic meaning of a sequence. It is not something very different from what you have already studied. The concept comes from a very old school chapter, which is functions. That particular chapter, if it is clear to you, the entire concept of functions is clear to you, a special way in which a function is defined is called a sequence. So, sequence is nothing but a special type of function. Now, let us talk about a function, and then I would be giving you the details about what a sequence is. Consider the set of natural numbers. So, inside it is sitting 1, 2, 3, 4, 5 and so on. And consider the set of all real numbers. Define a function f from collection of all natural numbers to the set of all real numbers such that f of n is 2n minus 1. So, I am saying define f from collection of all natural numbers to the collection of all real numbers such that f applied to any natural number is 2n minus 1. You know how you describe the function? That means what a function does, it associates members of the domain to the members of the codomain. In what fashion are the members of the domain of f, which is the set of all natural numbers, associated to the members of codomain of f, which is the collection of all real numbers? How is each natural number associated to members of the set of all reals is given by this very rule. It says that the natural number n under f is going to go to the real number which is obtained when you multiply that n with 2 and remove 1 from it. So, where will 1 go to? 1 under f will go to which real number, or 1 under f will be associated to which real number, or what real number will be the image of 1 under f? Image of 1 under f is f of 1. What is f of 1? F of 1 is 2 into 1 minus 1, f of 1 is 2 into 1 minus 1, 2 into 1 minus 1 which is 2 minus 1 which is 1. So, 1 is associated to the real number 1, 2 will be associated to the real number f of 2 will be 2 into 2 minus 1, 4 minus 1 which is 3. Then 3 will be associated to f of 3 is 2 into 3 minus 1 which is 6 minus 1, that is 5. Similarly, 4 will be associated to f of 4 which is 2 into 4 minus 1 which is 8 minus 1, that is 7. 5 will be associated to f of 5 which is 2 into 5 minus 1 which is 9 and so on. Right? Now, why did I pick up such a function? The speciality of this function is, first of all, the domain, and second of all, the codomain. I have defined a function whose domain is the set of all natural numbers and codomain is the set of all real numbers. Such function has a special quality attached to it. Firstly, any function defined on the set of natural numbers is called a sequence. Yes, this is how easy the definition of a sequence is. Nothing do you want, you just want a function which is defined on the set of natural numbers. That means any function f such that domain of f, what is this? Domain of f is set of all natural numbers is called a sequence. So right now what you can see over here is actually a sequence, because f is defined on the set of natural numbers, its domain is the set of natural numbers. So this f is definitely a function, but it is a special type of function known as sequence because it has its domain as the set of natural numbers. Now as I was pointing towards the collection of reals also, let me talk about that aspect as well. A function with domain as set of all natural numbers is called a sequence, and codomain as the set of all real numbers is called what? Till here if you see, function with domain as set of natural numbers, this much means that f is a sequence, this function is a sequence. But if the codomain is collection of all reals, that means the images of natural numbers, all the natural numbers under f are going to be real numbers. That means the range will be a subset of the collection of all reals. Right now also you can see 1, 3, 5, 7, 9, 11 and so on will be the images of natural numbers under f. These images if you collect, that is going to give you the range of the function f, and that is a clear-cut subset of the collection of all reals. So when you have the codomain specifically as collection of all reals, which means range is a subset of collection of all reals, that is range is a subset of collection of all reals, I say that the function is not just a sequence because its domain is collection of all reals, but because the images of natural numbers under that particular sequence are going in the collection of all reals, that means all the images of natural numbers are real numbers. So this sequence is called a real sequence. A function with domain as collection of all reals is called a sequence, but the moment you say that codomain is collection of all reals, which eventually means that range is a subset of all reals, which eventually means that the image of every natural number in the domain under this particular sequence is going to go inside the collection of all reals, that means it is a real sequence. Clear? Is called a real sequence. Fine. So you've understood what a sequence is. Sequence basically focuses upon the domain of f being equal to the collection of natural numbers. If along with domain of f being equal to the collection of natural numbers, codomain of f is also equal to collection of all reals, I say it is no more a sequence, it is a real sequence. So over here, my very f is not just a sequence because it is defined on the collection of all natural numbers, but also a real sequence because the image of all the natural numbers under f is going inside the collection of all reals. So I will say thus f defined from collection of all natural numbers to collection of all reals such that f of n is 2n minus 1 for all n in n is a real sequence. Now comes the representation of a sequence. Fine. You do not represent the sequence like this, like you represent functions conventionally. Of course, the concept says sequence is a function itself from the collection of all natural numbers to the collection of all reals if you're talking about real sequences, and that is what we would be primarily talking about. Our syllabus is going to naturally concern with the real sequences. So even when I say sequence, automatically I am not just fixing the domain as collection of all natural numbers, but I inherently mean that I am talking about real sequence. So you need to understand that the codomain is also fixed to be the collection of all real numbers. We do not represent our sequences like this. How do we represent? Let's get to the technique of the representation. Representation of a sequence. Let's see. Now what happens is, the moment you have a function defined from collection of all natural numbers to the collection of all reals, automatically the inputs are natural numbers and outputs are real numbers. See, the inputs are natural numbers, and when over the input f is being applied, output is a real number. Fine. You do not represent this particular association of natural numbers with real numbers with the help of the symbol f of n. You say that we write f of n as a of n, which further is written as a n for all n in n. Therefore, you do not say f of n equals 2n minus 1 is a real sequence. You actually say a with the small n written as 2n minus 1 for all n in n is a real sequence. So this is the very first thing to be noted. You do not use f, g, h symbols to generally denote your sequences. Your sequences get denoted in this form: small a n, small b n, small c n, small d n, like this. So if you have 2, 3 sequences with you, you would be denoting them by small a n, then the second would be small b n, third would be small c n, fourth would be small d n. So over here this happens. This is the first thing you have to note, that whenever you are going to have a sequence, it is going to be represented like this. Secondly, the images of every natural number under the function f. F of 1 will be written as a1. You can see f of 1 is a of 1, which is a1. So a1 will be f of 1. F of 2 will be written as a2. F of 3 will be written as a3, and so on. So what is this? a1 is the image of the natural number 1 under the sequence an, right? This is the image of the natural number 1. This is image of natural number 1, and this is called the first term of the sequence. Yes, first term of the sequence. When you are concerning yourself with sequences, there is ordering always defined. There is a first term, second term, third term, fourth term, fifth term, and so on. There is positioning of elements fixed. First term is the image of natural number 1. Second term is the image of natural number 2. Third term is the image of natural number 3. Fourth term is image of natural number 4, and so on till the nth term is the image of natural number n, and so on. So inside a sequence, each image that you get, see, you get images corresponding to every natural number, obviously, because you are defining a function. So function associates every member of the domain to some member of the codomain. That means corresponding to every natural number you will be having some image. The image of natural number n is the nth term of the sequence. So these natural numbers are actually giving that position to the image. If here some number is the image of 2, that means it is the second term. If there is some number which is the image of, say, 29, it is the 29th term of the sequence. So these are actually just sitting over here to give the positions to these elements which actually form the sequence. A sequence is different from another sequence when, use your common sense, you have one sequence defined from collection of all natural numbers to collection of all reals in this fashion, that 1 is being associated with 1, 2 is being associated with 3, 3 is being associated with 5, 4 is being associated with 7, 5 with 9, 6 with 11, and so on. Then you define another sequence again from collection of all natural numbers to collection of all reals, in which 1 is associated to, say, some other number, 2 is associated to some other number, 3 is associated with some other number, and so on. So what is the difference between the two sequences? It is not of the domain, not at all. Domain in both the cases is collection of all natural numbers. It is not of the codomain, because it is also collection of all reals in both the cases. What is different in the two sequences is the images of each natural number. The image of natural number 1 under the first sequence need not be equal with the image of the natural number 1 under the second sequence, and same with the other natural numbers. So what I am trying to say is the first, second, third, fourth and so on terms in the first sequence need not match with the first, second, third, fourth, fifth and so on terms in the second sequence. And that is what makes the two sequences different from one another. That means it is the images of natural numbers which are helping to identify and represent a sequence. And that is a key point. A sequence is represented with the help of the images of natural numbers. Whatever is sitting as the first term in the sequence, automatically it is the image of natural number 1. Whatever is sitting as the second term in the sequence, automatically it is the image of natural number 2 and so on. So, the second very note about the representation of a sequence is that the image of 2 under the function f is denoted by a2, and if this is the image of natural number 2, this is the second term of the sequence. Similarly, f of 3, which is the image of natural number 3 denoted by a3, it is the third term of the sequence. It is the third term of the sequence and so on. Clear? So we have understood that over here this was f of 1, f of 2, f of 3, f of 4, f of 5. Actually, I will be writing it as a1, a2, a3, a4, a5 and so on. a1 is image of 1, a2 is image of 2, a3 is image of 3, a4 is image of 4, a5 is image of 5 and so on. Clear? This f of n would be written as an. Fine. Now comes the third and the major part of a sequence. What you do is, this is something very nicely to be kept in mind. I am talking about the third observation or the third key point which is required to represent a sequence. What is that? We understood that the name of the function will be given like this if it is a sequence, and the terms which are coming as the images under the function which is a sequence will be given like this, and they would be representing this. Fine. Third point says a sequence, or let me write this particular sequence that we are right now dealing with. The sequence given by an equals 2n minus 1 for all n in n is represented as. How do you represent a sequence? You represent it like this, or like this, or placidly also you can just represent it like this, or like this. And that means the name of your sequence is an, and elaboratively it is equal to what? a1, comma a2, comma a3, comma a4, comma an, and so on and on and on. So what you do is you actually place all the images of the natural numbers under the particular sequence in their respective positions. Image of natural number 1 is kept at the first position. This is the first term of the sequence. Image of natural number 2 is kept at the second position. This is second term of the sequence. Image of natural number 3 is kept at the third position. This is the third term of the sequence. Image of natural number 4, a4, is kept at the fourth position. This is fourth term of the sequence, and that is what you do with all the terms. Nth term is basically kept at the nth position in the description of the sequence, and that stands for the image of the natural nth term. N natural number, basically it is the image of. So basically what we do is, because every sequence has one common thing, that the domain is correction of all natural numbers only. So a sequence is known, represented, identified by its images. If a, b, c are in GP and a to the power 1 by x equals b to the power 1 by y equals c to the power 1 by z, prove that these x, y and z quantities written over here are actually in GP. So we have a, b, c are in AP, we have to show that x, y, z, a, b, c are in GP, we have to show x, y, z is in AP. I am given that a to the power 1 by x equals b to the power 1 by y equals c to the power 1 by z. Suppose all these quantities are equal to k. This implies a to the power 1 by x is k and b to the power 1 by y is k and c to the power 1 by z is also k. If you take x power both the sides, you get a equals k to the power x, b equals k to the power y, c equals k to the power z. Here I have taken x power both sides, here I have taken y power both sides, here I have taken z power both sides. I have got this particular thing. Now I am given a, b, c is in AP. A, b, c, they are in actually GP. This implies b square equals AC. If three quantities are in GP, that means square of the middle term is equal to product of the first and the third term. So b square equals AC. B square means k to the power y whole square equals a into c, that is k to the power x into k to the power z, which implies k to the power 2y equals k to the power x plus z. Bases are same, we equate the powers, so you get 2y equals x plus z, which obviously implies that x, y, z are in AP. Because three quantities are in AP if and only if twice of the middle term is equal to sum of the first and the third term. So ABC were given in GP and that implied x, y, z are in AP. Clear? Moving to the next question we have, if n arithmetic means are inserted between 20 and 80 such that the ratio of first mean to the last mean is 1:3, then find the very value of n. Now I am taking this 20 as A and 80 as the quantity B. In this situation, I am saying let the n arithmetic means be A1, A2 and so on An, such that A, A1, and so on An, B, they are in AP with common difference equal to D, with D as the common difference. A I have taken as 20 and B is given to me as 80. This is a sequence which is an arithmetic progression. First term is 20, common difference is denoted by D. I know that what is the formula of D for this sequence to be an AP. If from A1 to An are the n arithmetic means inserted between 20 and 80, it is B minus A upon n plus 1. So it is 80 minus 20 upon n plus 1, that is 60 upon n plus 1. I am given that ratio of first mean to the last mean. This is the first mean, this is the last mean. Please understand the first mean actually is the second term of this AP and this is the n plus 1th term of this AP. This is the first term, then second term and so on. This is the n plus 1th term, this is the n plus 2th term. So first mean is the second term of this AP and nth mean is the n plus 1th term of this AP. I am given that ratio of first mean to the last mean is 1/3, which implies second term of this AP, its ratio with n plus 1th term of this AP is 1/3. Second term of this AP, you know, it is written as first term plus the common difference, and n plus 1th term is A plus n plus 1 minus 1, that is n, A plus nd, this is given as 1/3. What is A plus D? A plus D, A is actually 20 and D is 60 upon n plus 1. So you will be having 20n plus 20 plus 60. that is 20n plus 80. So 20 common, n plus 4 upon n plus 1, and a plus nd is a plus n times 60 upon n plus 1. This is 20n plus 20 plus 60n, that is 80n plus 20. 20 comes out, you get 4n plus 1. See, over here you get 20n plus 20 plus 60n. So, you get 20 plus 80n. 20 comes out common, 1 plus 4n. So, you get 1 plus 4n or 4n plus 1 upon n plus 1. Fine. You have that this ratio is 1 by 3. So, this ratio is 1 by 3, 20 n plus 4 upon n plus 1 whole upon 20 4n plus 1 upon n plus 1. Ratio of these two quantities is given to be equal to 1 by 3. 20 cancels out, n plus 1 is out. What are you left with? Because this is n plus 4 upon n plus 1 divided by 4n plus 1 upon n plus 1, that is n plus 1 upon 4n plus 1 if you multiply, and therefore you get n plus 4 upon 4n plus 1 equals 1 by 3, which implies 3n plus 12 equals 4n plus 1. Eventually you get 12 minus 1 is 11 and 4n minus 3n is n. So, n comes out to be 11. It is this value of n for which if n arithmetic means, it is actually 11 arithmetic means if they are inserted between 20 and 80, then the ratio of the first mean to the 11th mean will be coming out to be 1 by 3. Okay? Moving to the next question we have, if A, B, C are in AP and X, Y, Z in GP, show that this quantity is equal to 1. You just need to know the basics related to AP and GP and you would be through with any question on that. A, B, C are in AP. A, B, C, they are in AP. This means that twice of the middle term is equals to sum of the first and the third. X, Y, Z are in GP. This is if and only if square of the middle term is equals to product of the first and the third term. Consider the left hand side which you need to actually show to be equal to 1. It is x to the power b minus c into y to the power c minus a into z to the power a minus b. Let us manipulate according to our given facts. Y will be replaced by root z, root xz. If y square is xz, y will be replaced by root xz. So, I am going to write it as root xz whole to the power c minus a, z to the power a minus b. This can be written as x to the power b minus c, root x to the power c minus a, root z to the power c minus a, z to the power a minus b. Simplified further, this is x to the power b minus c, this is x to the power c minus a by 2, z to the power c minus a by 2, z to the power a minus b. Bases are same, add the powers. What do you get? X to the power b minus c plus c minus a by 2, and here you have z to the power c minus a by 2 plus a minus b. Eventually this gives you what? 2b minus 2c plus c, and then this is minus a upon 2, z to the power c minus a plus 2a, so this is plus a minus 2b whole upon 2, x to the power 2b minus a plus c whole upon 2, z to the power a plus c minus 2b whole upon 2. Please go back to the given facts. A plus c is same as 2b. So, this is 2b minus 2b whole upon 2, 2b minus 2b whole upon 2. This is x to the power 0 into z to the power 0, that is 1 into 1 and that is 1, that is what you wanted on the right hand side, and that is what proves your given question. Next we have A, B, C, D and P are different real numbers such that this expression is less than or equal to 0. Show that A, B and C and D are actually in GP. If I need to show that A, B, C, D, the sequence of 4 terms is in GP, that means I have to show the ratio of any term with its immediate preceding term is a constant. I have to show B by A equals C by B equals D by C. That's my aim. Right now we have A square plus B square C square into P square minus twice of AB plus BC plus CD whole into P plus B square plus C square plus D square is less than or equal to 0. If this expression is less than or equal to 0, just consider the left hand side of this given expression. A square P square, I am just writing it in the manipulated form. A square P square minus 2A PD minus 2A PD plus D square. Fine. Yeah. Next you have what? A square P square. Here you have A square plus B square. This is plus C square. So keep it as plus C square. Then you have plus B square P square plus 2BPC plus C square. Then you have plus C square P square minus, this is minus 2CDP plus, then you have D square. What actually I am trying to say is this is A square P square minus 2AP B plus B square. After that we have B square P square minus 2BCP plus C square. Then you have C square P square minus 2PCD plus D square. This actually is what? This is AP whole square and this is B square. Can I write this as AP minus B whole square? Right? Here you can write as BP minus C whole square and this will be CP minus D whole square. I am just manipulating the left hand side. When I do that, I know this quantity is greater than or equal to 0, greater than or equal to 0, greater than or equal to 0. Sum of 3 non-negative terms is always non-negative. 1 is giving you that this expression is less than or equal to 0. Then you manipulated and saw that actually it is greater than or equal to 0. By 1 and 2, you have that this expression is actually equal to 0 and this expression is nothing but this expression, that means AP minus B whole square plus BP minus C whole square plus CP minus D whole square is equal to 0. Sum of 3 non-negative terms is equal to 0 if and only if each of these terms is equal to 0. That means AP minus B whole square is equal to 0, which is only possible when AP minus B is equals to 0 and BP minus C is equal to 0 and CP minus D is equal to 0. Square of a real number is 0 if and only if that real number itself is 0. This implies AP is equals to B, or what I can say, B by A is equal to P. Then you have BP is equals to C, or C by B is equal to P, and CP is equals to D, or D by C is equal to P. That is D by C equals C by B equals B by A equals P. This means what? In order to show A, B, C, D are in GP, I needed to show D by C equals C by B equals B by A. I am getting D by C equals C by B equals B by A equal to the same quantity P. So this implies A, B, C, D are in GP. Clear? Next question says what? Let's see. F is a function satisfying f of x plus y is fx into fy for all xy in the set of natural numbers. F of 1 is given to you as 3 and summation fx x going from 1 to n is 120. Find the value of n. Please get this very, very clear that x and y are coming from natural numbers. You pick up any natural number, what is the feature? Suppose 7 I pick up as a natural number, 7 can be written as 1 plus 1 plus 1 7 times. 21 natural number can be written as 1 plus 1 plus 1 21 times. X is a natural number, it can be written as 1 plus 1 plus 1 x times, right? So, as x is a natural number, x can be written as 1 plus 1 plus 1 x times. Therefore, f of x is f of 1 plus 1 plus 1 x times. But it is given that f of addition of two things is product of the function being applied on those two things. So, f of 1 plus 1 plus 1 x times is f of 1 into f of 1 into f of 1 into f of 1 x times by the property given that f of x plus y is fx into fy, right. This means f of 1 whole to the power x, that is what happens, but f of 1 is given to be 3, so this is 3 to the power x. I have got f of x is actually 3 to the power x. Now, I am given that summation f of x, x going from 1 to n is 120. That means it is given summation 3 to the power x, x going from 1 to n is 120. Till now there is no relevance of AP or GP. If you open the summation up, you get 3 to the power 1 plus 3 to the power 2 plus 3 to the power 3 plus 3 to the power 4 plus and so on plus 3 to the power n is 120. The moment you see the left hand side, it is GP with first term 3 and common ratio 3. This is the sum of finite terms of a GP, sum of n terms of this GP, which is given by A. A is the first term, Rn minus 1 upon R minus 1. R is 3, common ratio to the power n minus 1 upon R minus 1. Fine. 3 minus 1 is nothing but 2. You eventually get 3 to the power n minus 1 is 120 into 2 upon 3. This is 80. So, you get 3 to the power n equals 81. 81 is nothing but 3 to the power 4. Bases are same. You equate the powers, you get n is equal